Oh, hi. I didn't see you there. I'm here working on my Marconi ground plane vertical antenna. Today we're going to be talking about how we're going to send a signal from this to the receiver. My Marconi ground plane vertical antenna sounds complicated, but it's really pretty simple. These four sticking out horizontally are the ground, and that means that the wave is going to propagate from the wavelength and not below this, because that's the ground plane. The RF waves are going to be sent through here, and they're sent as horizontal circles. And what we're going to be testing is how that signal and power diminishes to the other receiver, which is also a Marconi ground plane vertical antenna. But it's very similar to this. We're sending to that, and we'll be testing it.
So our objective here is to send a signal from our transmitter to our receiver down there and prove that the signal being sent will follow the inverse square law, or the power received by the receiver is going to be 1 over the distance squared. If we look into the inverse square law, we understand that as we go a certain distance away, our power received will always be 4 times less than the original power. And so when this happens, it will eventually follow up to the equation 1 over the distance squared.
For our procedure, we're going to use a RF function generator that will put out a frequency of 83.3 megahertz, which this will be connected to a transmitter, which transmitter will send the signal to our oscilloscope so we can get our radio wave. To build our transmitter, we're going to use styrofoam and brazing rods. The reason we use styrofoam is because it's invisible to RF frequency waves. Our rod length is 36 centimeters, and this will be putting out a frequency of 83.3 megahertz. The reason we use this frequency because we use the equations speed of light divided by wavelength, which equals the frequency. To obtain our data, we took 5 measurements in increments of 3 meters. We had one person standing here by the function generator, which this would send the signal every 3 meters to our receiver. This would send, we will have the oscilloscope to it to read the peak-to-peak values and the period. We repeated the same procedure, but this time we added a 10 dB amplifier to the function generator, which gave us our data. And then from there we took out our antenna and added a Venn diagram generator.
For our results and calculations, we took the data that we recorded over the 3 procedures, once without an amplifier, once with, and then a third time with the Van de Graaff generator. We graphed the voltage and the power. In order to obtain the power, we use the equation V squared over R equals the power, and we assume that R, or resistance in this, was 1 in order to normalize the data. We also took a look at the power gain in decibels, which is 10 log V out squared over VI squared, again assuming the resistance is 1. We recorded this data, graphed it, and checked it against an inverse square relationship in order to calculate error and just how close we were to the ideal results. Our results showed that the amplified signal with the high frequency RF generator had the cleanest and closest to an inverse square relationship. We found some discrepancies with the Van de Graaff generator. We also took more measurements with that, and we have a few ideas as to where those discrepancies came from, such as the hallway, which is where they seem to drop off, but we're going to need to come up with another hypothesis in order to test whether those discrepancies, that's what they came from or not.
In conclusion, we were able to successfully transmit a signal of 83 megahertz from the transmitter to the receiver. And we were also able to obtain quantifiable data from that. During the trials, we were able to not perfectly show an inverse square proportion, but we were able to get pretty close with the RF generator and amplified RF generator signals. The Bandy Graph generator did not show a inverse square proportion very well, and the things that could attribute to that are different doors being open, the hallway that's down this corridor. It's just a lot of things that could have just meshed into that, and it really didn't do well for us. But in a later experiment, we could get that to work out for us.